Okay, so in this video we're going to start off talking about the basics of circular motion. This unit is basically split into three different parts. We have circular motion basics, we have centripetal force and acceleration, and then we'll be talking about gravity. Okay, so in this video we're going to start off talking about circular motion basics. And when I say that, what I mean is we're going to be talking about basic concepts like arc length, angular displacement, radians. Well, if you don't know what a radian is, we'll talk about what that is. The concept of angular velocity, period, frequency. And what you're going to see in this unit is that there's lots of different equations, and that scares a lot of people, and it can be really confusing if you're just like focus on the equations themselves. I would highly recommend that you focus on understanding the concepts rather than memorizing equations. Okay, otherwise it looks like there's just a bunch of different equations, but a lot of them are actually related to each other and make sense if you understand where they come from. Okay, so just a word of advice there. Okay, so we're going to start off talking about the concept of angular displacement. Okay, so let's say, for example, we have a rotating arm which has 6 different paint cans along its radius. Okay, so we have a black, yellow, green, blue, dark green, and red paint can, and we open each paint can for exactly 1/4 of a revolution. Okay, now, of course, what's going to happen is they're going to leave little streaks of paint, like you can see here. Okay, and notice that each can is open for exactly 1/4 of a revolution, meaning that relative to the center of the circle, they have what's called the same angular displacement. In other words, if you were to draw a line from the center and trace out the angle from one side of the paint to the other side, they would all travel through the same angle. And here you should hopefully be able to see that this angle is 90 degrees because it's 1/4 of a circle. Okay, and so theta is what we call the angular displacement. Okay, so theta is the symbol for angular displacement. Okay, and here all 6 trails of paint represent the same angular displacement of 90 degrees or 1/4 of a revolution. Now, what is different about each trail of paint is that they have a different, what's called arc length. Okay, obviously the red line is longer than the yellow line. It's much longer than the black line, which is just like a glob of paint. In fact, there is no black line because the black can of paint was in the center of the circle. And so even though they have the same angular displacement, they have different arc lengths. Okay. And arc length is what we call S, which is kind of confusing because S has also been used in the past to represent displacement, like normal displacement. And so here, in the context of this unit that we're about to start, S is the symbol for arc length. Okay, that's literally the length of the arc. In other words, if you were to take any of these curved lines and make them straight and measure the length with a ruler, that length would be S, the arc length. Okay, so that's typically measured in meters, but it could be measured in any other unit of length. Okay, so we have some new symbols here. We have angular displacement, which is measured in or is given the symbol theta, which we've seen before. Theta is commonly used to represent an angle. And the units of angular displacement, the SI unit is the radian, which we'll come back to here in a minute. But angular displacement can also be measured in degrees or revolutions, like we saw with the paint cans. We talked about 90 degrees or 1/4 of a revolution. Okay, those are both different units for angular displacement, even though it's not technically the SI unit. Okay, angular displacement of an object moving in circular motion refers to the angle that the object moves through relative to a reference point in a given time. Okay, when I say relative to a reference point here, I meant like relative to the center of the circle, that angle that the paint cans move through. And then arc length we saw that's typically measured in meters. Of course, you can measure in any unit of length, centimeters, inches, millimeters, whatever. And the symbol for that is a lowercase s. It is confusing sometimes in physics that you have some symbols that repeat themselves, and so S is also the symbol for displacement that we saw last semester. Here in this context, it's used to represent arc length. And then this is just kind of a picture so you can see how all of these pieces kind of fit together. Yes, that length there is s, this angle here is theta, r is the radius of the circle. Now, you probably either know this already, or if you don't know this, it's probably common sense, but there is a relationship between the arc length and angular displacement of an object in circular motion. And that's probably pretty common sense. And again, if it's not common sense, it's probably something you notice intuitively, because you can see from the paint cans that if you go through a bigger angle, of course you're going to get a bigger arc length, right? Before we get to seeing what that relationship is, I want to tell you about radians and what a radian is. Okay, so a radian is an alternate unit for angle as opposed to degrees. Degree is basically defined so that you have 360 degrees in a circle. A radian is kind of more difficult to kind of give you a definition, but I guess one way of defining a radian would be to say that in one revolution, an object goes around one time in a circle. That represents 2 pi radians. And of course, that in degrees, we would think of that as 360 degrees. And so radian is just another unit for angle. And we're not going to get into where that comes from. It is kind of a more intuitive unit of angle once you get higher up in math. When you do more advanced trigonometry, like in pre-cal or in IB math classes, you'll do a lot of stuff in radians, because a lot of functions make more sense when you look at the graphs in radians. But a radian is just another unit of an angle. Okay, so 1 radian doesn't really represent anything by itself, but 2 pi radians represents 360 degrees. Or you could also say that 1 pi radian represents 180 degrees. Okay, so that's half of a circle, half of a revolution. So 1 radian is nothing. 1 pi radian, that is like 3.14-ish radians, would be about 180 degrees. Okay, so that is what a radian is. So before we get back to arc length and angular displacement, let's do some basic calculations with radians, from radians to degrees and vice versa. Now this is a skill that is essential for math. It's typically taught in math classes, especially when you get to the calculus level. And so if you don't know how to do these calculations, that wouldn't surprise me. But hopefully, if you are in these classes, if you have not seen this before in these classes, it will help you in these classes. Okay, and so in physics and a lot of the times in math, we typically want to express angular displacement in radians rather than degrees, and so we need to understand how to do those kinds of conversions. So the conversion factor we're going to be using is 360 degrees is equal to 2 pi radians, or 180 degrees is equal to pi radians. Either conversion factor gives you the same thing. Now, as long as you know that fact, you should be able to convert from radians to degrees or vice versa. Okay, so if I know, for example, that pi radians is 180, if you think like, what would 60 degrees be? Well, 60 degrees is a third of 180, and so 60 degrees would be pi over 3 radians. Okay, and so so on and so forth. Okay, so just to give you some basic examples of these conversions, convert 45 degrees into radians. If we have 45 degrees, the conversion factor I'm going to use is 180 degrees is in pi radians. And it's typical to leave your answer as a multiple of pi. So either you can just type this into the calculator, or you can just reduce the fraction. 45 divided by 180 is a fourth. Okay, so a fourth times pi radians, which is pi over 4 radians. Okay, and so that would be the answer to number 1. basic unit conversion as long as you understand the conversion factor. And again, going into radians, you don't. It's typical to leave your answer as a multiple of pi. Okay, it doesn't always have to be that way, but that's typical. Okay, if you reduce this down in the calculator, I wouldn't necessarily count off, but it's typical to express your answer, at least when you're going into radians, it's typical to express your answer as a multiple of pi. Okay, so pause there if you need to look at that some more. You can do one more example. Example 2. How many degrees are equal to 2 pi over 3 radians? Okay, so like any conversion factor, you start with what you're given, 2 pi over 3 radians. I need a little more space here. 2 pi over 3 radians. By the way, the symbol for radians is rad, R-A-D. Okay, so 2 pi over 3 radians. We know that the conversion factor is there's pi radians in 180 degrees. Okay, so a pi is going to cancel. 2 times 180 is 360. And then 360 over 3 is 120. Okay, this is really basic kind of unit conversion. These are the calculations you would be expected to either memorize or just be able to do very, very quickly by the time you get to calculus, especially if you take calculus in college. Okay, that they would kind of just assume that you know how many degrees are in 2 pi over 3 radians in college. Okay, so I would suggest you become very comfortable with these types of calculations or conversions. Okay, one more quick example, I think. A clock's hour hand goes through 1.5 revolutions in 90 minutes, and we're asked to calculate the angular displacement of the hour hand in degrees, and then the hour hand in radians. Okay, and if I'm not mistaken, this is actually a mistake. It should actually be, I think, the minute hand, not the hour hand. Because in 90 minutes, the hour hand only goes like 1.5 ticks. Okay, I think I actually meant this to be the minute hand. So, what is the angular displacement of the minute hand of a clock in 90 minutes? Well, 90 minutes is 1.5 hours. And so, let's think about what that is. 1.5 hours. In 1 hour, the minute hand goes around 1 time completely. Okay, and so 1.5 revolutions would be in 90 minutes, and we basically want to find that in degrees and radians. Now, there's 3 units for angular displacement. There's radians, there's degrees, and there's revolutions. Okay, the SI unit is radians. Radians is normally what you need to do calculations in, but here we're given the angular displacement in revolutions. Okay, so what is the conversion factor from revolutions to degrees? Well, you should know, of course, that 1 revolution is 360 degrees. They teach you that in like basic geometry. Alright, and so that would just be 540 degrees. And so I would say theta equals 540 degrees for the first question. The second question says, what is the angular displacement of the minute hand in radians? Okay, so 1.5 revolutions. What's the conversion factor from revolutions to radians? Well, 1 full revolution, by definition, that is 2 pi radians, because 2 pi radians is 360 degrees, which is also 1 full revolution. Okay, so 1.5 times 2 is 3, so that would be 3 pi radians. So for the second question, we would say theta equals 3 pi radians, and we're done. Okay, so that is example 3. Okay, so moving on. Let's see. Okay, so let's talk about the concept of angular velocity. Okay, now let me open up Notepad. Okay, so we know that if you have an object in constant velocity, we learned this like at the very beginning of the first semester, an object in constant velocity has an equation given by s equals v times t. Okay, so clearly this can be rearranged to get v equals s over t. And so for an object at constant velocity, this is basically the definition of velocity displacement over time. Okay, now there is an equivalent version of this for circular motion. Okay, so we have v, what we call linear velocity, and then we also have what's called angular velocity. And the symbol for angular velocity, so this is what we call linear velocity. This is what we learned about last semester. The symbol for angular velocity looks kind of like a W, but it's not. It is the Greek letter omega. Okay, so this is angular velocity. And the angular velocity of an object is defined as its angular displacement over time. Okay, so just like here, we have s over t. This would be theta over t. Although technically, I suppose it would be change in angular displacement over change in time. So this is how angular velocity is defined. Okay, how quickly is an object's angular displacement changing over time? Now, because theta is typically measured in radians, and seconds is typically measured, or time is typically measured in seconds, that means the unit for angular velocity, at least the SI unit, is typically in radians per second. Okay, so what does angular velocity represent? Well, it's just how fast is an object moving around in a circle. Okay, not in meters per second, but in some type of angle per second. Okay, so this is the idea of angular velocity, not to be confused with linear velocity, which is how fast an object would be moving in a straight line. Linear velocity is the velocity that we talked about a lot last semester. Okay, so the only velocity we've seen up to this point has been linear velocity, that's v. Not to be confused with angular velocity, which has the Greek letter, or which has the symbol omega, the lowercase omega, the one that looks kind of like a W, but it's not. Okay, so this is the concept of angular velocity. Okay, so pause it there and make sure you add that to your notes. Now, I will say one more thing about angular velocity. I said before in SI units, the unit for angular velocity is radians per second. But there's other possible units for angular velocity, just like you can measure linear velocity in miles per hour if you wanted to, even though that's not the SI unit. Okay, a more common unit for angular velocity that you might have heard of before is RPM. Okay, revolutions per minute. If you've ever heard of RPM, it's usually used for like motors or stuff like that. That is a unit of angular velocity. Revolutions per minute is a unit of angular velocity. It's not the SI unit of angular velocity, but it is a unit of angular velocity because you have some type of angular displacement over some unit of time. Okay, so RPM is a unit for angular velocity, which is not the SI unit for angular velocity. Okay, so here we have the concept of angular velocity. Make sure you add that to your notes. I'm going to erase this. Okay, there you can see what the Greek letter omega looks like. It does kind of look like a W, but kind of like a curvy W. Okay, so we have introduced the concept of angular velocity. I think I've already talked about most of these things already, although you can add them to your notes if you want. I talked about the units. It can be measured in RPM as well. It's a measurement of how fast an object is rotating. It's not a W, it's an omega. We can also relate what's called the linear velocity, which is the velocity we've seen up until this point, to its angular velocity. Okay, so what does that look like? Well, an equation I meant to talk about before when we talked about arc length, but let me go back. Kind of got too excited to talk about angular velocity, but we first started talking about arc length, okay, and I kind of alluded to there being a relationship between arc length and angular displacement. And the relationship between arc length and angular displacement is this: the arc length S is equal to the radius r times theta, where theta is the angular displacement. And this equation works as long as theta is in radians. Okay, I'm backtracking a little bit because I forgot to talk about this before, but I'll come back to linear velocity in just a second. Okay, so this should have been the first equation you put in your notes. I apologize. Okay, so S equals r times theta. Okay, this is the relationship between arc length, radius, and theta. And it's probably a pretty intuitive relationship. If you go back to the paint can example that we saw right here, we can clearly see that the paint can that had the biggest arc length was the one that was farthest from the center. Okay, so the red line was the longest because it was farthest from the center. It had the greatest radius. Okay, and so that relationship, S equals r times theta, that should make sense. Okay, so the bigger the radius, the bigger the arc length. Now, one more example of this equation, by the way. Let's say you have a circle and the radius is r. What do you call the arc length if you go all the way around the circle? Okay, that has a special name. Okay, the arc length of the entire circle is called the circumference. Right? You should have learned about that in elementary school. So if you go all the way around the circle, that means theta would be equal to 2 pi radians by definition, which means then you would have S equals r times 2 pi, or in other words, circumference is equal to 2 pi r. Okay, and so you've probably seen that equation many times before, but that is where it comes from. Okay, and so that's just a specific case of this equation right here. Okay, the arc length equation. Okay, so pause there, make sure you add that to your notes, and let's talk more about linear velocity. Okay, so we have S equals r times theta, but we saw before that if you take displacement and you divide by time, you get velocity. So if I just divide both sides by t, S over t becomes v, and on the right side, theta over t is a quantity we talked about just a few minutes before. That is angular velocity. Okay, that is my omega. Okay, and so this equation relates linear velocity to angular velocity. So at this point, you should have 3 equations written down: the arc length equation, the definition of angular velocity. You can include the deltas if you want, it doesn't really matter. And then the equation that relates linear velocity to angular velocity. Okay, so at this point, you should have these 3 equations written down. Okay, now I've talked about what angular velocity is and the units that is measured in. What do I mean by linear velocity? Well, I can be really specific with linear velocity. Give me just a second. So if you imagine, let's say there's a bug on the rim of this wheel that's spinning around. Okay, how fast it's spinning is the angular velocity, right? That's delta theta over delta t. If the bug were to fly off the wheel, let's say the wheel is spinning so fast that the bug flies off, how fast the bug is moving in a straight line, that would be the linear velocity. In other words, how fast would that object be moving in a straight line if it were to be released from the circular motion? Okay, so that is why it's called linear velocity, as opposed to angular velocity, which is how fast the angular displacement is changing. Okay. Another example of that would be if you imagine tying a ball to a string and spinning the string around in a circle, if you were to cut the string, the ball would fly off in a straight line. However fast the ball is moving at that point, that is what we mean by linear velocity. Okay, at any given point, an object with circular motion is going to have an instantaneous linear velocity, meaning if it were to stop moving in a circle, it would fly off in a straight line. The direction of that velocity is always tangent to the curve. And keep that word in the back of your mind, it'll come back later. Tangent to the curve. You might have even seen that word before in one of your past math classes, tangent. Okay, so if you're spinning a ball attached to a string and you cut the string, the ball is going to fly off tangent to the circle, okay, in a straight line. Okay, we'll come back to that word tangent later. Okay, first we're just going to do a few basic examples and then we'll stop the video. Okay, so example 1. A clock's minute hand moves over an angular displacement of pi radians in 30 minutes. Okay, makes sense to me because half an hour it would move across half of the revolution, which would be pi radians. And the first question says calculate the arc length traveled during this time for a minute hand that is 10 centimeters long. So when you're doing these conversions, you need to make sure you convert your units correctly. Centimeters should be converted to meters. Unless it tells you otherwise, you should always convert to SI units. Okay, so there's only one equation for arc length, S equals R times theta, but this equation only works if theta is in radians, which luckily we're given theta in radians. So S equals R times theta, that would be 10 centimeters times pi radians, and so that would be 10 times pi centimeters, but we need to convert that to meters, so we move the decimal place 2 times. So that would be 0.1 times pi meters, and if I stick that into my calculator, I get 0.31 meters. So that is the answer to the first question. Notice I need to round my answer here because I have to, I can't leave my answer for arc length in terms of pi because then it'll have an infinite number of sig figs and I can't have an infinite number of sig figs. Okay, I should have 2 sig figs here. Okay, so 0.31 meters. For the second question, it says calculate the angular velocity of the minute hand in radians per second. Okay, so now you're probably looking at all your equations and you're like getting a little flustered, like, oh, the 2 of them have angular velocity, which one do I use? Well, think about what you're given. You're given a time and you're given an angular displacement, so you should probably use the angular velocity equation that has those things. The definition of angular velocity is the rate at which your angular displacement changes over time. Okay, and if we want that in radians per second, then we need the angular displacement in radians, which it is, and we need the time in seconds, which it's not, but that's a pretty easy conversion. We can convert time to seconds really easily. 30 minutes, there's 60 seconds per minute, so that would be 1800 seconds. And so the angular velocity would be pi radians, so pi divided by 1800, and then I just need to type that into my calculator. Okay, so pi divided by 1800 is going to be 0.0017 radians per second. Okay, so that is my omega. And if that seems like a small number, think about a minute hand. You can't really see a minute hand moving unless you look at it over, an extended period of time. Okay, so it makes sense that that angular velocity should be very slow. And then the last question says calculate the linear velocity of the end of the minute hand in meters per second. Okay, so linear velocity is v. Okay, so v equals r times omega. If we want this in meters per second, that means we have to have the radius in meters. The radius in meters, if you divide by 100, you get 0.1 meters. And so that would be 0.1 times 0.0017. And that would be 0.00017 meters per second. And again, that seems slow, but it is slow. I mean, a clock's minute hand isn't the fastest thing in the world, right? Now, what does that linear velocity represent? That means if there was like an ant hanging on to the end of the minute hand, and the minute hand is going like around in a circle, if it were to fly off, not down to the ground, but let's say if you hold the clock horizontal, if the ant were to fly off, I don't know why it would fly off at that speed, that's really slow, but if it were to fly off in a straight line, it would be moving 0.00017 meters per second in a straight line. Okay, so that is example 1. Pause there if you need to look at that some more. Okay, and I think I just want you to try to do example 2 on your own. It says a motor spins at 20 revolutions per minute. Calculate the angular velocity of the motor in radians per second. See if you can figure that one out on your own. I'll put the answer so you can check your work. Okay, so we're now done with about the first half of this third of the unit. We will finish up this third of the unit in the next video. As always, please let me know if you have any questions, and I'll see you guys in the next video.